We are all set. Yeah.
Okay, thank you so much. Thanks for inviting me to get out of my boring lockdown life to give this talk. I'm very excited to do that. So, as stated, I'm from the University of Western Cape, which is one of the three universities in the Greater Cape Town area. So here's a picture of Cape Town with Table Mountain, and the University of Western Cape is located somewhere behind the mountain as you go away from the city north towards Itemba Labs, which is our national accelerator facility. The university is situated exactly between the city of Cape Town and Itemba Labs on the N2 highway. And I'm going to talk about three examples of experiments we did, but not at Itemba Labs, experiments we did elsewhere in collaboration with our North American and European colleagues. Basically emphasizing on stringently testing our understanding of nuclear structure, in particular nuclei that are essential for fundamental symmetry tests. And there is some sort of a link between the three. Hopefully I can do all of three. If not, I'll just stop at two if I run out of time. So please excuse me for that. So let me just start with a brief introduction. I don't know what is the audience demographics here, so I might be start with a little basic introduction, if you please bear with me. Essentially, what do we mean by fundamental is essentially what I understand it is in terms of size scales. So this graph essentially tells you the size scales that physicists deal with, starting with 10 to the minus 16, 10 to the minus 18 for quarks, all the way till the edge of the universe, roughly 40 orders of magnitude higher. And what we mean by fundamental is that if you understand the physics mechanisms at the very, very small size scales, essentially it is the dynamics and the interplay of these fundamental particles and their interactions that lead to the diversity of phenomena you see at large size scales. You may not be able to explain all of it using these theories, but it's these fundamental interactions that lead to everything we see and beyond. So that's what I mean by fundamental. And we all know that at the very, very basic fundamental level, the theory is best explained by the so-called standard model of particle physics, which classifies particles as quarks and leptons, and their interactions occur by exchange of these bosons, W bosons, Z bosons, photons, and gluons. And the quarks and the leptons are further classified as left-handed doublets and right-handed singlets. But what's interesting and what has always baffled physicists is that we cannot have a similar description for neutrinos. You will see here, you have a right-handed quark, quark doublets and singlets here, but there is no right-handed neutrinos because there is no experimental evidence of right-handed neutrinos to date. The V minus A interaction is almost exact as far as experiment goes. Parity is maximally violated, and neutrinos always come with a certain helicity or chirality. So it's a very chiral theory when you talk about neutrinos, and it's very mysterious. And there are lots of open questions that pertain to the understanding of, to our understanding of neutrinos. Why is parity maximally violated? Is it probably a low energy limit of something more profound? Are neutrinos Majorana or Dirac? Why are the neutrinos masses so small, and why we cannot describe their mass generation using the standard Higgs mechanism? Are they related to the observed matter-antimatter asymmetry in the universe? Is there a CP violation in the leptonic sector that could lead to this baryon asymmetry? There's a lot of open questions that makes neutrino physics very interesting. So we are nuclear physicists, and this is where atomic nuclei reside in this size scale. And we know that atoms are made up of nuclei, and nuclei are made out of nucleons, protons, and neutrons. But if you get inside the nucleon, it's a very complicated structure by itself. A nucleon doesn't just comprise of valence quarks. There's a sea of quark-antiquark pairs, lots of gluons, a very strongly interacting system, very complicated. But the advantage is that in an atomic nucleus, you have three of the known fundamental forces that play a very, very important role in all nuclear processes: strong interaction, electromagnetic interaction, and weak interaction. So this interplay of forces allows you to make really, really precise tests of our fundamental understanding of matter using nuclear physics techniques. And I will give you a couple of examples. However, it always should be taken into consideration that is a very, very difficult to understand system simply because of the complicated nature of its structure, even at the nucleon level. So the three examples I'm going to talk about are, I'm going to talk a little bit about some work we did pertaining to the beta decay of neon-19, which is essentially a measurement, a precision measurement of the beta decay rate. And some experiments we did pertaining to the neutrinoless double beta decay of a much larger system, 136 xenon decaying to 136 barium without the emission of any neutrinos. And I'll briefly, if time permits, I will talk about some recent work we did pertaining to, a standard laboratory source, sodium-22 beta decay, and why is that interesting in terms of such kind of studies. But in all these three cases that I'm going to talk about, it is vital to know that no matter what you do, you have to have an understanding, a proper understanding of the structure of this nuclei, because they play a critical role in these sort of measurements. Just a quick review. Like I said, parity is maximally violated in beta decays. That is a known fact that is incorporated into the standard model. Here is, I just wrote down the Lagrangian, a shortened version of the Lagrangian, which has an electromagnetic interaction. And this is the weak interaction part, which contains the charged part and the neutral current part. And it's assumed that the weak interaction that goes into the electroweak theory is maximally left-handed, only left-handed chiral fields in both charged and neutral current sectors. However, during the early 70s, by Jogesh Pati and Salam did some research, and they found out that it's possible that this maximal parity violation, this left-handed nature of weak interactions, could be a low energy limit of a more fundamental theorem, which allows you to have left-right symmetric extensions. So there are right-handed currents, there are right-handed neutrinos, you just haven't seen them yet. And these have been extended in subsequent work by these authors. And they all say that the right-handed weak interactions could be a possible mechanism that exists, but it's suppressed because of the large, heavy right-handed bosons, which have not been observed so far. So they postulate there are right-handed W and Z bosons that we haven't observed so far, and they're so heavy. And because they're so heavy, it suppresses the neutrino mass. And that's why neutrino masses are so small. In this context, the decay of neon-19 is a very powerful probe to look for right-handed weak currents. I'm just quickly showing you the decay of neon-19, the beta decay, before I get into the details of our experiment. So neon-19 is an isospin half, 1/2 plus nucleus that decays via a mixed super-allowed transition to the ground state in fluorine-19. This is the mirror nucleus of neon-19. This is 99.988% branch with a small forbidden branch to the 1/2 minus state at 110 keV, and a small branch to this 3/2 state. So you don't see many gamma rays when you observe the decay of neon-19, because it predominantly goes to the ground state. And how do you want to probe for right-handed currents using nuclei? Holstein and Treeman in the 70s gave us a formalism which relates the right-handed coupling constants, the right-handed physics, to observables in terms of these so-called spectral functions, F1, F4, and so on, which are related to the vector and the axial vector, or the Fermi and Gamow-Teller form factors for the decay. This is an example from a recent experiment at Triumph using the TriNat laser atom trap, recently published in the Physical Review Letters, in which instead of neon-19, they took a radioactive ion beam of potassium-37, trapped it using a laser trap, and polarized it using laser, so that all of the potassium-37 atoms were spin polarized along one direction. It's a classic Madame Wu experiment using fancy laser traps. You polarize the potassium-37 and you see how many betas go along one direction as opposed to the other. And this experiment placed the most stringent limits on right-handed currents. And the right-handed currents are parameterized using these two parameters, X and Y, which are written in terms of delta and psi. The delta is the ratio of the right-handed boson to our known left-handed gauge bosons, and psi is the mixing angle. So they mix like quarks. They have a left-right mixing. There's a small mixing angle, and so these parameters parameterize the right-handed currents. This goes into the spectral functions. They add to the known form factors of Fermi and Gamow-Taylor, and they will show up as a beta asymmetry in the measurement. This was work done by a group in Belgium, in which they did a whole bunch of calculations to see which nucleus is most sensitive to right-handed currents. So here you can see potassium 37, which has a beta asymmetry parameter of minus 0.5720. But you can see this the lastmost column is a sensitivity to right-handed currents. And you can see this is potassium 37 is roughly 60 to 70 times less sensitive than neon 19. Neon 19 is probably, to the best of my knowledge, the most sensitive probe to right-handed currents within atomic nuclei. And this is because of the structure. And what happens is there is an accidental cancellation in the matrix elements, which makes there's a cancellation in the left-handed sector for the matrix elements that doesn't exist in the right-handed sector. And this accidental cancellation due to the structure between the form factors makes it highly sensitive to right-handed currents. Okay, so the procedure is you measure the beta asymmetry, A beta, which is essentially the asymmetry in the beta direction, the asymmetry with the momentum with respect to the spin polarization, which is F4 divided by F1. It's this coefficient that's multiplying the spin polarization part time the momentum. You measure that and you see if you agree with the standard model prediction or not. This is, it's a very, very hard measurement because the beta asymmetry is so small. Here you can see the beta asymmetry is 0.03. It's roughly 3.9%. And everywhere else, it's much, much larger. And because it's so small, it's so sensitive. But because it's so small, it's also hard to measure. So it has been measured several times, 1963 by Cummins and Dobson. And then subsequent times, it has been measured by the same group at Princeton. And they always got answers that were not really in good agreement with one another. But you can see here, this one has A beta 0 and this one has A beta. A beta 0 is essentially the beta asymmetry for zero kinetic energy. So they plot the beta asymmetry as a function of the kinetic energy of the positrons, and they find the intercept for that, the zero intercept for that, and that's that. And that is the integrated value. So if you want to put these both numbers in the same footing, you want to convert them to what you would call the axial vector coupling constant divided by the vector coupling constant. But since it's a t equal to half to t equal to half transition, the vector form factor is 1. So essentially you can write it down just as the axial vector. You can see here, if I translate each one of these A betas to a C, then this one is not as well in agreement with the others, but others are roughly, they scatter around the same point here. Now, are these good enough to make, to put useful limits on right-handed currents? Not really, because there are two parameters here. So you need two measurements. Here, there's only one measurement. And you need to put limits on two parameters. You need to make one more measurement. And the other measurement is the ratio of C to A. But since A is 1, the other measurement is C, the axial vector form factor, which can be obtained by taking the FT values of purely Fermi, purely vector beta decays to the FT value of neon 19. So you need a measurement of R and you need a measurement of A beta. Now, the numerator in R is very, very well known because of a sustained campaign to measure these FT values for super allowed Fermi decays. So all you need to know is this and this to get useful constraints on right-handed currents. And here again, you will see the X and the Y come in if there is new physics. So for this, you need a high precision measurement of the 1/2 plus going to the ground state 1/2 plus transition rate. Okay, so that's one motivation to measure neon 19 beta decay very precisely. The second thing, where neon 19 again plays an important role, is that although our knowledge in the charge current sector of the weak interaction is very, very well known, our knowledge of the weak interaction in the neutral current sector, especially within nuclei, between nucleons, nucleon hadronic weak interactions, is very, very, very scanty. And that's because the quarks within a nucleon interact with each other with a parity violating weak interaction that doesn't change flavor here. So it's a flavor conserving parity violating quark-quark weak interaction. But since it's happening in this really messy nucleonic environment with a lot of gluon exchanges and strong interactions, it's really complicated because the physics here is very non-perturbative. So it's hard to calculate stuff. So it's not very well established how the strong interaction effects affect the weak interaction physics within a quark and a quark neutral interaction. In the 1980s, there was a theory that developed by Planck, Donoghue, and Holstein, who used the meson exchange model, similar to what you would do for a strong interaction process, in which this nucleon-nucleon quark interaction was modeled phenomenologically using a strong interaction parity conserving vertex and a weak interaction parity violating vertex. And they went from the quark-quark level to the nucleon-nucleon level by dressing for the strong interaction and modeling it by the exchange of these pi, rho, and omega mesons. And the paradigm was that this interaction, the isovector component of the weak interaction, dominated the neutral current part. So you look for isovector neutral current interactions. Experimentally, you can do that by looking at the scattering of longitudinally polarized protons over different targets, or looking at the circular polarization of gamma rays, or capture of polarized neutrons on protons, and looking again at the polarization gamma ray asymmetries, looking at left-right asymmetries to see if there is parity violation. If there is parity violation, then you can see if you agree with your calculations, and see if your theory of understanding of the theory is correct. However, it's really hard because, well, okay, good. No, I'm gonna go back a little bit. In the recent past, this was the paradigm, and there was absolutely no results. Nothing came out. When people measured this stuff, the observables were very small. They couldn't really rule out anything on the basis of their understanding. However, in the recent past, there has been a lot of development in theory in terms of the state-of-the-art theory methods in using effective field theory-based model-independent methods to calculate this aspect of the weak interaction done by these authors here. And there was a very, very precise experiment of the polarized neutron capture on protons that came out as in a recent PRL. And there has been some progress in understanding. However, the challenge still remains that you're looking for a weak interaction effect in a very strongly interacting medium. So your signal will go as H weak over H strong, which is roughly 1 part in 10 billion. So it's a very, very small signal you're looking at. And these theories have indicated, and this experiment have indicated, that our previous understanding using this meson exchange model has been misplaced, and we don't have to look for now the isovector part of the neutral current interaction, but there are isoscalar contributions as well. So there has been a re-emphasis on our understanding of this, and people have wanted to look at it differently. There's a lot of theory that has been developed, but unfortunately there's not enough experimental data to see if the theory is right. And this is where, again, neon 19 can play an important role, because atomic nuclei can be used as amplifiers to amplify this 10 to the minus 7 signal. And this amplification comes from parity doublets in nuclei such as neon 19, which goes to fluorine 19. So here, fluorine 19, you have this 1/2 plus 1/2 minus parity doublet separated by 110 keV. Here is fluorine 18. There's a 0 plus 0 minus parity doublet separated by only 39 keV. And there is this, if there is a parity violating interaction between the nucleons, these two states will get admixed. Of course, this matrix element is very small, but the energy denominator is also very small, which leads to an enhancement. Furthermore, there will be an interference between, if you measure the gamma rays from these transitions, there'll be an interference between E1, the regular E1 and the irregular M1 transitions. And this interference also leads to an enhancement. And here you will see this has been a measurement in fluorine 19, 2 measurements, and you can see it's more than a factor of 10 compared to what we had expected here. Here it was 10 to the minus 7. Here we see an enhancement. Our signal is roughly 10 to the minus 5. The interesting thing is here, the mixing is just purely isovector. And the new theory shows that the isovector doesn't play a big role. It's mostly isoscalar and isotensor contributions to the parity violating neutral currents that play a good role. So this fluorine 18, although it has a small energy denominator and a large enhancement, it's not really interesting anymore. Here, because there's an isoscalar and isovector contribution, it's interesting to remeasure this. But despite the fact that these are extremely light nuclei, and theoretically they should be very tractable to calculate this mixing matrix element, it was shown some time ago that depending on how you do the calculation, this matrix element differs by factors of 15, 20, 25, 30 sometimes. So it's a huge model dependent thing, even for a very, very light system such as fluorine 19. But he also showed in this paper that you can calibrate your calculations by measuring this beta decay branch. So essentially, you're looking at the mixing between this 1/2 minus and this 1/2 plus state, this parity mixing, this matrix element. You want to calculate that, but you can calibrate, you can very accurately calculate that by calculating this and calculating this matrix element, and then measuring this matrix element from the 1/2 plus 1/2 plus, and taking the ratios. So you measure this, divide by the matrix element, then you calculate it, take the ratio of the beta decay branch to the matrix element, compare to measurements, do the calculations, and you can really get values for parity mixing matrix elements that are within 10 to 15%. So that's another motivation to measure this 1/2 plus to 1/2 minus branch. Not only will you measure a very, very accurate 1/2 plus to 1/2 plus branch for the right-handed problem that I talked about before in the charged current sector, this is also important to calculate this parity mixing for the neutral current kind of measurements. So neon 19, I don't know, somehow seems to be very, very ideally suited for any parity violation experiments using atomic nuclei. So that's another motivation. So we need to measure this transition rate to the ground state very accurately by measuring this transition rate reasonably accurately, because it's hard to measure ground state to ground state transition rates. So this experiment we did at Triumph using the old 8pi detector. This is an example of the ISAC 1 and ISAC 2 facilities at Triumph. You have roughly 500 MeV protons coming from the cyclotron. It smashes into a large target, a silicon carbide target that's heated, and then the neon 19 is mass separated and it goes to this RFQ, and it comes out here where the 8pi is located. The 8pi is an array of 20 Compton suppressed, used to be an array of 20 Compton suppressed germanium detectors with an inner array of 20 scintillator paddles made out of plastic scintillators with a tape that was made out of aluminized mylar. The beam came in at very low energy, 37 keV, and this is a picture of the array opened up. It has a tape system to implant the beam, and the tape circulates through these tape cassettes. And the idea is to take short bursts of beam. So we were taking very, very short bursts of beam and then counting for like 15 or 20 half-lives, and then cycling the tape, another short burst of beam, count for 15, 20 half-lives, cycle the tape. We measured the betas using the scintillators, and that was used to determine the half-life of neon 19. And the gammas were used to measure the branching ratio. And together we would get the FT value for the decay. So this is work published a few years ago. We measured the half-life using different, so that the challenge in half-life, high precision half-life measurements is that there's this dependence on dead times. Your rate is changing as a function of time, your dead time changes as a function of time. So you impose an external dead time that is much larger than any of the preceding electronics at the last stage of the data acquisition. And then you determine that very precisely, and you obtain the half-life by doing the dead time correction. And we saw this systematic effect in which we saw that the half-life, extracted half-life, seemed to be dependent on this externally imposed dead time that went like that. And then we, on further investigation, found out that actually these scintillators were after pulsing. So you were getting a prompt pulse, and then after 500 nanoseconds, you were getting this late pulses, late scintillation pulses that were not real. And once we corrected for that using a Monte Carlo simulation based on this TDC spectrum of the after pulsing, we saw that the half-lives all agreed. And this resulted in a very, very precise half-life measurement, which was followed up by 2 more measurements of the half-life. And this tells you about the significance of this work. All 3 turned up to be PRL publications, and then 1 more followed up by Ganil as a PRC. And if you combine all of this, you have a 0.01 relative uncertainty measurement in the half-life. The branching ratio turned out to be a lot more challenging because there are no gamma rays to monitor drifts and things like that that you usually encounter with gamma ray measurements. There is only this huge 511 that comes from annihilation. There's some X-rays, there's 2 Compton shoulders, there's a backscatter peak, and nothing else. So this took a long time to analyze, but eventually we did complete the analysis of this data to measure this 0.01% and 0.02% branches, which would result in a strong 1357 keV gamma ray and a strong 110 keV gamma ray from the first excited state. These are the 2 gamma rays clearly observed. There were a lot of systematic effects that needed to be taken into consideration to have a real precision gamma ray measurement. And the idea, the technique we used was to take the gamma rays were measured with beta gamma coincidences, but we were also recording the beta singles in the scintillators. And if you take the beta gamma coincidences to the ratio with the beta singles for each tape cycle, in each tape cycle, you take this ratio, you cancel out a whole bunch of systematic effects. Of course, there's more systematic effects that need to be taken into consideration that we had to evaluate using Monte Carlo methods and other things. All that, it resulted in a correction K, which was a product of several corrections: a correction due to coincidence summing, a correction due to random coincidences, pile up, dead time. There is a small Q value dependence on the beta efficiency in the scintillators, and statistics and efficiency. So you can see these are all numbers close to 1, but they're not really 1. So that goes into this K1. And once you factor that in, you get a precise branching ratio measurement for these excited states. And then you do 100 minus that, and you'll get a branching ratio measurement to the ground state. Okay. So just a quick comparison here. This is what was before. So we made a factor of 3 improvement in the branching ratio to the first excited state. And now, together with the precise half-life measurement, the branch is known with this much of precision, 99.9878 plus or minus 0.0007%. Okay. And the FT value has now been improved by a factor of 3.5. Okay. So what does this result in? This is, if you remember, this is the graph I showed of the Berkeley and the Princeton measurement that were done all the way from the 60s to the late 90s of the beta symmetry for neon 19 beta decay, which was further used to extract the axial vector coupling constant, the gamma of Taylor matrix element. And this is what we got. If we use our measurement, then this is what the standard model predicts. SM is what the standard model predicts, and the band is the uncertainty in the prediction. So clearly, it doesn't agree with any of these measurements. Does that mean they're right-handed currents? We don't think so. If we use our mixing ratio, our branching ratio measurement to get a mixing gamma of Taylor to Fermi mixing prediction and use that to get VUD, then this VUD, the up-down matrix element of the CKM matrix, which is supposed to be unitary, if we use these three numbers, then we disagree with unitarity by more than 5 sigma. So that's not true. So these three experiments can be ruled out, okay? This one can also be ruled out because this also violates CKM unitarity at the 99.6% confidence level. That only leaves the 1975 measurement. That is a reasonable measurement in terms of CKM unitarity. And CKM unitarity is, there is no violation observed to date. So after a lot of precise probes, so that seems good. So essentially, it's only because of our precise measurement that we obtain this, and we can rule this out, all these three out. And we're using just, we can ignore this one because it's not that precise, but you're using just this value, we get, which is this one. If we compare our standard model prediction, it's in reasonable agreement. There's not that much of a deviation anymore. And you can see that here in the picture. Our prediction and the experiment are not that much in disagreement anymore. So that's good. Here again, I'm plotting the delta, which if you remember is the ratio of the right-handed to left-handed gauge boson squared. And here is the left-handed to right-handed mixing angle. And this is what was published by Triumph in 2018 from their potassium 30 data, which is this band here. And this was the most stringent limit on right-handed physics at the 90% confidence level. And this is what we get using our measurement and the experiment 1975 measurement by Calaprice et al. And if we combine these two, firstly, I'm just going to summarize. This stringent limit happened because we got this highly strict FT value measurement, and we also obtained a forbidden decay rate that is 10 times lower than shell model calculations that needs to be further investigated. And we have theory colleagues who are investigating this. But if you combine these two, this is available in this work by Bernadette Ribeiro. But if you combine these two plots, you will see that here is the exclusion set by potassium 37 by the Triumph measurement. This black stuff is ours. So as a result, we have ruled out most of this part, most of this part, and most of this part, making it one of the, and most of this part. So this is the region where delta and psi have non-zero values at the 90% confidence level. So this is one of the most precise limits to date. And okay, so that was our neon 19 measurement. And I'm just going to quickly, how much time do I have? Hello?
15 minutes more.
Okay. Okay, I'll quickly talk about my another measurement. There's a connection between right-handed weak interactions and neutrinoless double Bayer decays. There is a very popular theory that is an extension of what Mahapatra and Senjanovic postulated, called the seesaw mechanism, which allows for right-handed interactions. These heavy right-handed bosons cause the smallness of the neutrino mass, and they could cause neutrinoless double Bayer decays. And if neutrinoless double Bayer decays occur, then a neutrino is the same as its antineutrino. The neutrino and an antineutrino under charge conjugation are similar properties. And the mechanism is in the following, that the observed neutrino eigenstate is actually the ratio of this MD squared divided by MR. And because MR is very large, your neutrino mass becomes very small. This is the famous seesaw mechanism for generation of neutrino masses. And if this were true, you should be able to observe neutrinoless double Bayer decays. One of the most promising neutrinoless double Bayer experiments is the decay of 136 xenon to 136 barium. Just showing you here, 136 xenon is more bound than 136 cesium. So this is energetically forbidden. So you're allowed to make a double Bayer decay from 136 xenon to 136 barium. And currently, there's several experiments, there's at least 3 I know of that are looking for this neutrinoless double Bayer decay. One is the NXO experiment, the other is the Kamlan-Zen experiment. And this is a very, very promising example. One of the reasons it's promising is because the standard model allowed 2 neutrino double Bayer decay half-life for this decay is much longer than any of the other cases. So it's highly suppressed, and that's because of the structure. So if you're looking for the signal here, that's the neutrinoless double Bayer decay signal. This standard model background is much suppressed, so it's not going to contribute here. And this standard model background you cannot get rid of. It is the ultimate background that cannot be gotten rid of, no matter how much shielding you use, it's there. So it is highly suppressed. And the other advantage is that this uses liquid xenon as a time projection chamber. This is another experiment that's looking into this, the next experiment. But you can tag on the daughter barium ions, and if you tag on the daughter barium ions and do coincidences, if that's possible, then your room background is going to virtually go to 0, because you're going to do coincidences for every proper decay. So that many other examples that do not offer this advantage. So that's another advantage for 136 xenon. However, it's well known that even if you do observe a neutrinoless double Bayer decay, to do anything further than that, you need to know the matrix element for the decay, and that you get only from theory. And unfortunately, there is a lot of discrepancy in the extracted matrix element for the decay. So here there are several theoretical tools, many body approaches used to calculate this neutrinoless double Bayer decay matrix elements. There's a non-relativistic energy density functional, relativistic energy density functional, QRPA by Vascula, Tübingen, Chapel Hill, IBM, Shell model, Michigan, Shell model, I don't know where that is. I think it's Strasbourg, Madrid. So there are a lot of people doing these calculations, but you can see there's a huge spread in the calculated value for the matrix element, and the half-life goes as the matrix element squared. So if this factor of 4 here, it'll become factor of 16 here, and that will affect your extracted effective neutrino mass, your extracted limits on CP violating phases, or anything that you need to do extra from these neutrinoless double Bayer decay measurements. Here is a paper by A. Gando et al., which was the most stringent limits set by any neutrinoless double Bayer decay measurement on the effective neutrino mass. And you can see here, that's the band. And that band, that uncertainty in that band in an upper limit comes purely from the spread in the matrix element evaluated for 136 xenon. Okay, but it's interesting that 136 xenon is n equal to 82. So it's a nearly spherical parent and also a nearly spherical daughter. I'll just get into that in a little bit. So this, I'm just now focusing on the nuclear matrix element for 136 xenon. The popular 2 methods are the Shell model and the QRPA, historically and traditionally. But this was in the recent past, and then suddenly, as the calculations got more and more complicated, more and more extensive, the numbers got smaller and smaller. So this took into account deformed Wood-Saxon QRPAs and deformed Hartree-Fock-Bogolikov QRPA and large basis Shell model calculations. And these are hugely different from what we have here. In fact, the discrepancy is more than a factor of 4.2. So this is something that needs to be looked into, and people have been looking into this. One of the fundamental assumptions that people take into account in some of these calculations is how they consider the pairing between light nucleons in the parent and the daughter. And the QRPA, usually the QRPA takes into consideration what is the BCS approximation, in which the nucleons are correlated, highly correlated pairs. They form Cooper pairs and they're sloshing around in this superfluid kind of an environment. They all couple to spin 0, and the Fermi surface in the parent and the daughter look smeared like that with a Fermi gap, and this is a well-known approximation that they use. Incidentally, these calculations here have been shown to be mostly smaller than these calculations, because at n equal to 82, you cannot have a Fermi surface that is smeared like this. There's a sharp cutoff to the Fermi surface, which curtails the wave function when you sandwich the operator between the two states. So that is an approximation that many calculations take into account, and we need to see if this approximation is correct. And the way you can investigate the validity of the BCS approximation or BCS pairing, well established for several years, and it's beautifully explained in these two references, is by studying the nuclei using two nucleon transfer experiments such as PT, TP, helium-3N. And if the nucleus is a purely superfluid Cooper pair-like nucleus, then there'll be a strong population of the ground states and very weak population in the excited states. It's all going to stay in the ground state, the cross section, okay? If you look at, so in the pure superfluid limit, if it is purely superfluid, then you will see as 0 plus to 0 plus couplings in the double Bayer decay. So the matrix element, if you decompose the matrix element in nucleon pairs that couple to spin 0, and other nucleon pairs that don't couple to spin 0, and the dominant contribution is going to come from spin 0 couplings. And then there'll be cancellations by non-spin 0 couplings. And this has been shown by both shell model theorists and QRPA theorists. You see a J equal to 0 contribution, and then small cancellations due to J not equal to 0 contributions. Okay, this is similar to, you know, 2 particle 2 hole and 1 particle 1 hole enhancement cancellations, like shell model theorists like to explain. So there is a large J equal to 0 coupling, and then there's cancellations. In the recent times, Alex Brown and collaborators showed that if you want to calculate a neutrinoless double Bayer decay matrix element, say from going from germanium-76 through an intermediate nucleus arsenic-76 to selenium-76, you can go do it this way. You can go 2 neutrons less plus 2 protons. So you can decompose the matrix element in terms of 2 nucleon amplitudes, 2 neutron removal amplitude, and a 2 proton addition amplitude. And you can directly correlate that to PT, TP, helium-3N type of experiments. And quite remarkably, these calculations also show that, again, the nuclear matrix element is dominated by the ground state in the intermediate nucleus, which in this case is germanium-74. And then there are cancellations from other J not equal to 0 states that are dominated by 2 plus contributions, very similar to here. So we decided to go ahead and do some experiments to see if the understanding of the theory of these nuclear matrix elements is on a secure footing. We went ahead and did that at a high resolution spectrometer. Unfortunately, this facility has shut down, but the uniqueness about this facility is they have a tandem, which gives you very precisely known beams, and they have this high resolution Q3D spectrograph, 3D spectrograph, which consists of 1 quadrupole and 3 dipoles. And this is the scattering chamber. The beam comes in from here. There's a scattering chamber, and there's a spectrograph. It can be rotated to several angles on a plane. This is the focal plane detector at the spectrograph. The ejectiles, in our case, 138 barium PT. The ejectiles come out, the tritons, they go through these foils. They have 2 sets of proportional counters through which you can do a delta E measurement, and then the ejectiles stop in a scintillator, which you see another delta E for identification of the ejectiles. Then you can, discriminate against the deuterons and the tritons and the alphas and so on. This is the spectrum we got for 138 barium PT. Remember, 138 barium PT goes to 136 barium, which is the daughter of 136 xenon neutrinoless double Bayer decay. Also, it's interesting that 138 barium is N equal to 82, similar to 136 xenon, so it's nearly spherical. And then we went ahead and, did an analysis. We did proton-proton scattering, decided on the best optical model potentials, and analyzed all these states that we observed. We saw a whole bunch of new 0+ states, which shows that there's a whole bunch of excited 0+ states. Remember, they're correlated to the 0+ pairs in the BCS approximation. So the states labeled in black are the ones that have been previously known. We added to this knowledge by adding all these 0+ states. And we saw a huge fragmentation of the ground state strength to these two excited states. You could call them, some people call them pairing vibrational states. I'm not a big fan of that convention. So I'll just say that there's a large fragmentation of the strength. We don't know why there is. It could be that the deformation of these excited states matches the target. We don't know that. That needs to be investigated. But there is a breakdown of the BCS approximation. There's a 53% relative branch to all these 0+ states, which is pretty large. Then we went ahead and collaborated with Alex Brown from Michigan State University, who gave us 3 interactions that he uses, that are generally used for neutrino-less double Bayer decay calculations, matrix element calculations, the TIN 100PN, T100T, and GCN 5082, which is used by mainly by the French group. And this is a running sum of our measured cross section at very, very forward angle, so L equal to 0 for the 0+ states. And this is what Alex Brown calculates using a large basis shell model calculation that incorporates these 5 orbitals between n equal to 50 and n equal to 82, using a 2-step fresco. So he took the wave functions. He used these calculations to get the wave function for the target, 50 0+ states in 136 in barium, going through an intermediate state in 138 barium using multi-step transfer. There was a factor of 2 discrepancy in our measurement and his calculations. And if you look at the comparison here between the measurement and calculation, the discrepancy is mostly at the forward angle. Is the L equal to 0, where the discrepancy is the largest. What could be the problem? If you add the contributions of several orbitals from beyond the valence space that connect to your state through the pairing interaction, and there is this correlated, you could have correlated pairs going all the way up, and you include them in a higher order perturbation theory treatment, and you include these coherent contributions from orbitals beyond the valence space, then you will see that the L equal to 0 PT cross section shown here can be reproduced with experiment. So he did that, and then he corrected the 2 neutron transfer amplitudes. And then now our agreement is within 10 to 15% instead of a factor of 2. Okay. Now 136, remember that he go through the intermediate nucleus like this and get the neutrino-less double Bayer decay matrix element. So how do we do that now? Now we know that 136 xenon going to the intermediate nucleus, 134 xenon, is very similar to what we did, 138 barium to 136 barium, n equal to 82 to n equal to 80. The deformations are similar, the change in configuration is similar. There has been theory work done in this regard long back. It has been verified by relativistic mean field calculations and experiment, NN prime gamma experiment. The structures are very similar. So if you incorporate similar calculations that we needed to reproduce our experiment data, then we get new values for the matrix elements, at least for the J equal to 0 part. So here I'm quickly summarizing the results. This is what used to exist before using the QRPA calculations. The matrix element was 2.18 with 23 orbital QRPA calculation. This work shows that with 28 orbitals, we're getting a reduced. Again, you see this consistency. As your calculation gets more sophisticated, the matrix element reduces. There is the J equal to 0 contribution. There is the J not equal to 0 contribution. There's this cancellation, and this is the net effect. Similarly, the Strasbourg-Madrid group obtained this for the J equal to 0, 5.72, J not equal to 0. And we obtained J equal to 0, 3.73 without incorporating these core polarization effects from beyond the model space. But once you incorporate the core polarization effects, then the J equal to 0 increases, needs an enhancement by roughly 1.6, which takes this value to 8.96, which is pretty large. And this has been obtained purely on basis of comparison with our experimental data. I'm just going to take 5 more minutes to conclude. So we now have revised nuclear matrix elements, at least for the J, but we can also do more. Eventually, these calculations also need information about the nucleus. You see here 136 xenon, the calculations go like that. They go through the intermediate nucleus and down to 136 barium. But most neutrinoless double barrier decay calculations incorporate something called the closure approximation, because of the uncertainty principle, the momentum of the neutrinos are very large, so they connect very large high energy states. So theorists just put an average energy for the intermediate nucleus, but knowledge of the intermediate nucleus will be further useful in reducing the uncertainty in the matrix element. Recently, there was this work done by the Kamlan-Zen collaboration in which they precisely analyzed the 2 neutrino double barrier decay spectrum. And they have so much data now that they can really test their model. And they are now sensitive. The shape, the distortion in the spectrum is sensitive to leading order, sub-leading order matrix elements. So next order matrix elements, which are represented by these Xi 2 nu 3 1 terms. And depending on how they do the calculation in the shell model, you see here the blue is the shell model using one interaction, the black is the shell model using the other interaction, the GCN interaction, which I showed you before in our calculations. And you see there's a discrepancy again, which doesn't quite agree. So there is, even in the 2 neutrino part, there's a discrepancy when you're looking at next to leading order contributions. And this discrepancy can be resolved by better understanding of the intermediate nucleus. Prior to 2009, nothing was known about the intermediate nucleus. In 2011, there was, some information came out. And in 2011, there was this helium-3T work done by RCNP, which was done at high energy. So it produced a whole bunch of 1+ states that are necessary for 2 neutrino double barrier decay matrix element calculations. We went back to Garching to Munich to do this experiment, again using the same target, but using a deuteron being D alpha that sends it to 136 cesium. And this is the 136 cesium spectrum we obtain, a very, very high resolution. And you need high resolution for this because it's an odd heavy nucleus, a lot of density of states. The blue labels are the ones that we have observed before. Everything else have been observed for I think the blue ones are the ones that were observed here at the RCNP, and everything else has been observed newly for the first time. We did some DWB analysis. We agree with what's known from before, more or less. The angular distributions are in very good agreement. And this analysis is going to be published soon. In conclusion, our 138 barium PT work indicates a large breakdown of the BCS pairing approximation. We also did a similar analysis for 136 barium PT and show that this persists. A similar approximation breakdown of BCS pairing persists in 134. And it's quite likely that there are there's a deformation contribution because it's in the shape transitional region, these barium nuclei for n less than 82. Somebody needs to do some Kulex analysis of this, but we are going to leave that for other collaborators. Shell model analysis together with Alex Brown showed that after taking into account core polarization corrections to the 2 nucleon transfer amplitudes, we find a large enhancement in the J equal to 0 contribution to the neutrinoless double barrier decay matrix element. And this also converges and agrees with a large model space QRPA calculation. This is the first time that a part of a neutrinoless double barrier decay matrix element was estimated using actual experimental data, I believe, to the best of my knowledge. And this provides an important step for similar estimations to the canceling contributions. And we also performed, for the first time, a high resolution spectroscopy of low lying states in 136 cesium, and we are engaging with theory colleagues now to finish up the manuscript. I'm not going to talk about sodium-22 because I ran out of time. So I think I'll stop here. Thank you. Thank you very much.
Thanks, Smarajit, for a very nice talk. And maybe some other time we'll listen to your other work on sodium-22.
Okay, thank you.
Now I'll request people to raise their hand in the Zoom, and then we can take a few questions.